Check it out now, y'all.
nanoHUB-U, online instruction.
Welcome to Module 3.2. And as you may recall from the last module, what we discussed was one application of these general equations that we developed last week. And this is a one-dimensional problem. And in a one-dimensional problem, it's relatively straightforward to write down the Hamiltonian and the sigma matrices that tell you the connection to the contacts. And we use that to discuss this problem of a wire with two scatterers. And the important point was that while one scatterer would have given you a transmission that would have looked kind of monotonic, reduced relative to the ballistic one, when you have two scatterers, you tend to see these peaked things. And the point I stressed was these peaks arise from this wave nature of electrons due to this interference, constructive and destructive interference. And these are real things in the sense that people have designed special devices where these can lead to some very useful observable effects. And this is discussed a little bit in this homework problem 1, which I discuss in tutorial 3.1. But the point to note is that while you can have special devices where this is indeed observed, normally this is not what you see at all. What I mean is, after all, if you take any wire, it usually has a whole bunch of impurities like this, various defects where electrons get scattered. And ordinarily, we do not think of this interference between scatterers. You see, if interference between scatterers played such an important role, then you wouldn't have Ohm's law. You wouldn't have this idea that resistance increases linearly with length. Because if you think about it, supposing I got one scatterer, and it gives me a transmission of T, let's say. So for just one scatterer. So I would say, well, conductance is Q squared over H times this transmission. You see, that's what I had argued earlier when you look at this equation, that from here, if you calculated conductance, it would have been Q squared over H times this transmission. Right? Now, if you turn that around, you could call it this resistance. It would be like H over Q squared times 1 over T. And one of the important points, I guess, that we discussed a lot in part 1 of this course, and this is the thing that is discussed in the first 5 lectures of the notes, is that of this resistance, H over Q squared is associated with the interface, and the rest is actually associated with the scatterer itself. So, if you just had one scatterer, so let me call that, say, T1, just as a reminder that's for 1, you could write it like this, and you could write this as -1 plus 1. I have not changed anything, but the advantage of writing it this way is you can think of this part as the actual resistance of this scatterer and this part as your interface resistance. Well, so if you had 6 such sections, or let's say just 2 such sections maybe to keep it simple. If you had 2 such sections, what you'd expect is, well, the resistance of 2 sections, I guess I could put a R1 here just to remind me that this is resistance of one section having a transmission of T1. So if I had 2 of them, it would be, again, this standard quantum of resistance times this part would get doubled, assuming they were the same, they had about the same scattering strength. So it'd just be this times. So you'd have 2 times 1 minus T1 over T1. You see, 1 over T1 minus 1, you could write as 1 minus T1 over T1. And then plus whatever the interface resistances. And that's, of course, the same interface resistances here. That's it. So with R2, you'd expect something like this. And from this, you could deduce what should be T2, you see, because R2, of course, should be related to the transmission through two scatterers by the relation. And so that tells you what the transmission of two scatterers is compared to one scatterer. I could cancel that. And the relation you'd have then is 1 over T2 is equal to 2 minus T1 divided by T1. It's just a little algebra. You see that? And if you turn it around, it tells you T2 is equal to T1 divided by 2 minus T1. And so if the transmission through one scatterer, one of these, is T1, then the transmission through 2 would be related to that by a relation like this. Okay. Now, what that means is, if one scatterer has a transmission looking like this, two of them would be related in a simple way to that. And if you calculated it, it would have looked just something a little bit smaller. That's all. And then if it was three scatterers, a little bit smaller. So the point is, it would still be a simple monotonic curve like this, not things that show peaks. On the other hand, if you use the quantum method that we discussed, where you have all these wave interferences and things like that, when you have multiple scatterers, you tend to calculate transmissions with all kinds of sharp peaks. So there would be a peak here, maybe another peak somewhere here, another peak someplace there, all kinds of peaks. Depending on how many scatterers you have, move them around, it will change quite a bit. And so the question is, which is real? And of course, the point you realize is that Ohm's law usually holds. I mean, that's what we generally believe in. So ordinarily you expect there to be a simple connection between, what you see for two scatterers to what you see for one scatterer and so on. And the reason you normally never see things like this is because of dephasing processes. That is what I started to explain at the end of the last module, that usually, of course, in this solid, these atoms are not sitting in a fixed position rigidly, but are actually jiggling around. And because they are jiggling around, these resonances are also sort of jiggling around all over the place. And so in practice, all these interference effects that the quantum theory includes are really not seen directly. Now, one thing I should mention is that when you do a one-dimensional problem, usually these quantum effects, these peaks, this is a whole lot more accentuated or seen much more clearly than if you were doing a problem that was like two-dimensional, which means it is not just a single wire, but you had multiple things like this. And how you do that, that's something I'll explain a little better in the next module. We'll go to that. But usually what happens is, you see, the reason you have peaks, the way you think about it, is that take this off. Way you think about peaks is, as I mentioned in the last module, it is as if two of these scatterers kind of put the electron in a little box. And so the electron wave has to fit into that box. And if the electron wavelength fits, that's where you have a peak in the density of states, and that is why you have a peak in the transmission. And in tutorial 3.1, I explain how you could use that to understand the location of the peaks. So the argument usually would be that if this distance is, say, d, then k times d should be equal to some integer times pi, because k is like 2 pi divided by the wavelength. So this is equivalent to saying that this distance should be some multiple of half a wavelength. Okay? Now the thing is that when you have a two-dimensional conductor, then let's say this direction is, we call x, and that direction, let's say, is y, then the appropriate condition in this case is more like kx times d is equal to n pi, where kx is the x component of k. See, and that looks like kd cosine theta equals n pi, where theta is the angle at which the electron is traveling. That's this angle. So what that means is, if you have electrons going at different angles, which actually corresponds to these different modes that we discussed in part 1, and which I'll explain a little better in the next module. We'll talk more about it. But when you have electrons at different angles, each one has a different condition for giving you a peak. So what that means is, you don't get such sharp peaks necessarily anymore, because different electrons at different angles have different peaks, and so it all gets smeared out, usually. So what happens when you go beyond one dimension is that the difference between the quantum and the semi-classical, or the simple one, is not all that pronounced, but it is still fairly pronounced, though. It is still quite evident. So let me explain what you see usually. When you have when you go beyond one dimension, this quantity actually gives you what we generally call this transmission, and I write it with a bar on top. Because when I write T without a bar, what I mean is transmission probability. That means if an electron comes in, what's the probability it gets to the other end? And probability should be less than 1, like it's somewhere between 0 and 1. Whereas when I write this, it is kind of like the product of two things. One is the number of modes, and then there is the transmission probability. So you can approximately think of it that way. Because this number of modes are all these different channels that the electrons are able to conduct through, and each one has a certain transmission probability. And so, the thing is that in the quantum formalism, if you didn't think about all this and just calculated that quantity, what it would give you is something that you could interpret as number of modes times transmission. Which means if it was a ballistic conductor, this quantity would have been equal to the number of modes. This would tell you directly how many modes you have, actually. So usually this is the number you're talking about, and the point is often in white conductors, this number of modes is very large, hundreds. And so when you plot T bar, a ballistic conductor might have, say, a fairly large value for T. So I guess it would also be varying with energy. So I'll just draw some such thing, something here. But the point is, this number is something like hundreds or thousands, some big number, not 1. And what would happen if you calculated this quantum mechanically is that you do see fluctuations around there. See? And these fluctuations are usually, the size is about 1. So what that means is, of course, if this is 100, then 1 out of 100, it's like a 1% fluctuation in there. On the other hand, if it's 10, then this would be about 10% or so. So what people have studied all this, and this is something that back in the late 80s and early 90s, people studied a lot. You see, and there would be all these conductors where they would take it down to low temperatures, and at low temperatures, when they measured the conductance, you see, as a function of the location of the chemical potential. So supposing the chemical potential you move up and down, and depending on where you are, you'd see a different conductance, and it would fluctuate. And people would see this at low temperatures. Okay? And then if you raise the temperature, come up to room temperature, then you wouldn't see it. And then if you again took it back to low temperatures, you'd again see a pattern like that, except that usually once you bring it down, it would be a different pattern. And the reason people believe it's a different pattern is that when you bring something up to room temperature and then take it back down, the impurities move around. So you might still have 20 impurities in there, but they're not in the same positions they used to be, and so their interference pattern itself has changed. See? On the other hand, as long as you stayed at low temperatures, you could measure it day after day, and you'd always get the same pattern of fluctuations. So all these things actually were studied widely, back in, let's say, late 80s and early 90s, and is fairly well understood. Another interesting thing that actually, which was understood even before this, the fluctuations were understood, is that the average quantum value is usually a little less than the semi-classical value. Namely, this black curve which you get, if you ignore interference completely, usually gives you a bigger conductance, bigger transmission, than the average you'd get by doing a quantum calculation. So this is what's often called the weak localization effect. Again, I'm not going into the physical reason for all this. That again is another effect that took, some time for people to understand. But the main point I wanted to make here is that when you do a quantum calculation, you tend to get a lot of these interference effects, which you often wouldn't see at room temperature, at least. And if you went down to low temperatures and did it on small enough samples carefully, you might see them. Right? But if you're trying to understand experimental results at room temperature, then it is almost like if you did a simpler theory, one that didn't invoke the wave nature of electrons, you'd have got an answer that would have looked much more like experiment. Whereas if you do the full quantum theory, you might get things that don't look as much like experiment anymore. Okay. Now, so one question that comes up is, how can we include this dephasing effect into the equations that we talked about, such that you'd be able to incorporate dephasing in our calculations, so that when you do the quantum calculation also, you wouldn't necessarily get this, which comes from ignoring dephasing completely, but you could gradually in your models turn on more and more dephasing and get the semi-classical result. How do you go from here to here in your models in a continuous way so that you can model real experiments? Now, the way it can be done, I want to explain that a little bit, is the following, and that is that, you see, the sigma here, if you notice, has one component due to the contact 1, another due to contact 2. And what we do is, we add a third component, sigma 0. Let's see. And this represents the interactions with the surroundings inside the channel. So it is like the sigma 1 is here, sigma 2 is here, and the sigma 0 is like in the channel region right here. You see? Sigma 0 is right here in the channel region. Okay? And that tells you about the interaction with the surroundings. And similarly, there would be a corresponding thing that you'd have to add to this one. This is the in-scattering part. Okay? Now, what makes this calculation a little more complicated is that, let me explain the basic method that's used, that could be used here, is that sigma 0 is equal to some constant. Actually, let me write this here. The sigma 0 is equal to some number, d0, some constant, times gr, where gr is given by that equation. Now, what that means is that when you are calculating gr, you see, you cannot calculate it directly. Previously, it was like, I know sigma 1, I know sigma 2, put it in, invert, and you have gr. Now, what happens is, even the right-hand side has something that depends on gr, which means the calculation has to be done what you call self-consistently. That is, you usually assume some value for sigma 0, like in the beginning, let's say, assume it's 0, calculate GR, put it back in here, calculate GR again, with the new GR you get, put it back, and keep doing it till it converges. So that's the process that's used for doing this. And the point I want to make is that this will get, depending on the strength of D0, it will give you dephasing in the model. That is, if D0 is 0, you're back to coherent processes. If your D0 is, as you increase it, there's more and more dephasing. And here again, the extra term that you add is D0 times Gn. And this also now becomes a self-consistent calculation, because this equation number 2, this one, has to be solved self-consistently with this, just as 1 has to be solved self-consistently with this. Okay. Now let me just quickly try to motivate where this idea comes from. We won't really go into it in any depth, but let me just quickly explain the idea. And that is, if you remember, the way we got equation number 2 was by starting from the Schrödinger equation and saying that you have to add a sigma to denote the connection to the surroundings, and then you have to add a source term. And then the idea was that the strength of the source, SS dagger, that is what we call sigma in. Now, supposing there is a scattering potential, that is, what that means is when the electrons are going through the channel, it feels some potential due to the surroundings. Okay? And due to the scattering potential, if you ordinarily put it in, you'd put it in here. You'd put H plus US. That would be the strength of the scattering potential. But supposing, instead of thinking of it in H, we think of this additional term as another source term. So that is, we don't keep it here, but instead we add the US psi over here. Then you see, when you do SS dagger, you'll also get a term like US psi times US star psi dagger, which is like US star, that's the strength of the scattering potential times psi dagger. And this is the quantity that, of course, we have called Gn. And this is the quantity, that's the D0. So this D0 is a measure of the strength of that scattering potential. And the potential has the energy, has the dimensions of electron volts. So D0 has the dimensions of electron volt squared. So that's this D0 Gn that I explained here. See? So this is just to give you a heuristic feeling for why you have a term like this, and how something like this accounts for a scattering potential. And of course, when you add something here, there's a corresponding thing that has to be added here in order that overall electrons don't disappear. So what I mean is, if you just add a source term, then there will be continually electrons going in. But by having a sigma here, it ensures that electrons are also taken out. And what is shown in the notes is that this combination automatically makes sure that if we calculated the current, you see this I, this expression usually used to calculate the current at the real terminals. But if you used this expression to calculate the current at this terminal represented by sigma 0, then this particular choice will ensure that the current at that terminal is 0, as it must be. Because after all, electrons cannot be disappearing here. There is no real terminal there to extract electrons. So this choice ensures that that current will be 0. So overall then, this is the basic method that one could use to calculate to include dephasing into these models. Now, of course, there are other numerical issues that one may have to think about when trying to implement this in a real device model. Because, for example, in order to use this, you need the entire full Green's function. Green's function is a matrix. Whereas, often, there are many numerical methods that take advantage of the fact that you may need only the diagonal elements of the Green's function. And you don't want to calculate the rest of it because that slows down the entire computation significantly. So there are considerations like that might dictate whether you want to use this method or not. But as far as the kind of simple problems that we are discussing in this course is concerned, the computation time is not really an issue. These matrices are relatively small, 100 by 100 at best, and it's not hard to include this dephasing. And one of the examples that's given in the homework problem, and this is discussed in tutorial 4.2, where I show how by using this particular choice of D0, you actually recover the semi-classical results in a clear way. Semi-classical means the ones that ignore phase. And by using a different type of D0, you could also get things that not only take care of the phase, but also give you some amount of additional momentum relaxation as well. But these things are discussed in tutorial 4.2.